Hello all, I Ritvik Bhadra, Assistant Professor, HIT Kolkata, welcome you again back to my lecture number 4, which will be on boost converter. I hope everybody has understood the operation of the buck converter in detail. If you have any doubts, please use the comment section of the last lecture and ask your questions related to the topic. In understanding the boost converter or a step up converter, we will apply the same methodology. That is, we'll do the circuit analysis first, then draw the relevant waveforms, and at last derive the necessary equations that will be required to solve problems related to a boost or step up converter. So let's jump into the topic and understand the basic operation of the boost converter. Hence, I have drawn the basic circuit of a boost converter over here, which consists of a DC source Vi in series with an inductor. Then there is a single pole double throw switch with a one fixed point S and two throws A and B. The B point is connected to the resistive load, and across the load a capacitor is connected to reduce the voltage ripple. Please assume all the directions of current, that is IL, IC and I0, shown in the circuit to be positive. And if the current IL is in the direction as shown in the figure, then the left hand terminal of the inductor will be positive and the right hand terminal will be negative. So this inductor voltage drawn in the figure will be treated as positive. Now next what we will do, we will analyze the circuit during two positions. One is dt, that is t on, and the other one is 1 minus d into t, that is t off period, like as we had analyzed during the buck converter. So let's start with the dt period. During the dt period, you know that S will be connected to A point. Hence, this circuit will look as follows. The B point is disconnected. If you observe the circuit, the current starts flowing from the source Vi, flows in the clockwise direction, charges up the inductor, flows from S to A and back to Vi negative. Hence, we will apply KVL in the above circuit. Since the current flows in the clockwise direction, we will start from Vi. So, Vi minus the drop across the inductor, that is VL, is equal to 0. So, VL comes out to be Vi. Now, Vi is a constant DC voltage. Hence, VL magnitude will also be a constant, which is equal to Vi. Next, we will represent this VL value, that is Vi, in the waveform. So, now observe the diagram or the waveform which I have drawn for VL. Since VL was found out to be a constant value of magnitude Vi, I have drawn the Vi parallel to the x-axis during my dt period. Next, we will find the equation for IL, the inductor current, and then try to plot it. We know that the generalized equation for IL is given by VL by L into T, and as calculated, the value of VL during dt period came out to be Vi. So, substituting it, we will get IL is equal to Vi by L into T. So, again it is a y equal to mx equation. So, straight line having a positive slope of Vi by L. Again, we should take another consideration, that is inductor current is continuous. Hence, I have drawn the IL figure on the right hand side. As IL you have already calculated to have a positive slope or an increasing slope of Vi by L, I have shown IL to be an increasing slope during dt period of Vi by L. Now we will calculate the value for ISA and ISB. If you look into the circuit, ISA is nothing but the inductor current IL or the source current IS. Hence, ISA can be written as equal to IL. And since the B point is not connected in the circuit, ISB will be considered as 0. Next, we will plot the values of ISA and ISB as calculated. Since ISA is equal to IL during dt period, it will have a positive or a rising slope of Vi by L as indicated in the waveform. And since ISB is equal to 0 during dt period, I have indicated 0 by making the x-axis bold and written the value 0 during dt period. Next, we will calculate the value of voltage VSA, which is given as Vs minus Va. As you can observe, the circuit S and A point are short circuited with one another. So, both will have the same potential. Hence, Vs minus Va will give to be 0. Thus, VSA is equal to 0. Hence, representing VSA as 0 on the waveform by making the x-axis bold, during dt period and writing a value of 0. Now calculating the value of VSB. I have drawn the B portion in the circuit again for you to understand in a better way. So VSB can be written as Vs minus Vb. Again, you know S and A point are at same potential, and as A is connected to ground, Va will be 0, therefore Vs will also be 0, and B point is connected to the positive terminal of the load voltage, so Vb can be written as V0. So VSB is 0 minus V0, that gives you minus V0. Now representing VSB during dt period in the waveform. As you have already calculated, VSB comes out to be minus V0, and V0 is a constant output DC voltage. So we will show VSB as a straight line parallel to x axis but in the negative direction of magnitude V0 during the dt period as shown in the waveform. Now next we will study the region during 1 minus dt period or T off region. During this region, the S point is connected to B and the circuit looks like as shown in the figure. In this case, the inductor will discharge, and as we know, since the inductor current is positive, it will retain its direction in the same direction as it was flowing when S was connected to A, that is in the clockwise direction or from left to right. So IL is shown left to right over here, but the inductor polarity changes. So the right hand side of the inductor becomes plus and the left hand side becomes minus. Now the source along with the inductor supplies the energy to the load, which is R naught. So now applying KVL during this period, we will get Vi plus VL minus V naught is equal to 0. Bringing Vi and V naught on the other side, we will get VL is equal to V naught minus Vi. Again, since the inductor polarity has changed, so the displayed value of the inductor voltage will be negative. So taking minus common, we will get minus of Vi minus V naught. Therefore, I have plotted VL during this period as Vi minus V naught in the negative direction as shown in the figure. Next, calculating the value of IL during this period. You know IL is equal to VL by L into T, and substituting the value of VL as calculated as minus of Vi minus V naught in the equation. So we can find our y equal to mx equation again, but it is having a decreasing slope because the value of VL is negative. Thus I have shown IL as a straight line having a decreasing slope of minus Vi minus V naught by L during the 1 minus dt period. Next, calculating the value of ISA and ISB. Since A point is not connected in the circuit, there will be no current flowing from S to A. So ISA is equal to 0. And as you can observe the circuit, ISB, that is the current flowing from S to B, will be equal to IL, the inductor current. Thus plotting the two values, what we get? ISA is equal to 0. So during this period 1 minus d into t, I have made ISA 0 by making the x-axis bold and marking 0 over there. And ISB is equal to IL, which means IL is nothing but a decreasing slope of the value shown in the waveform. So I have shown ISB is also having a decreasing slope during this period. Next, calculating VSA. VSA is equal to Vs minus Va, you know, and A point is connected to ground, so potential at A, Va will be 0, and B and S are short circuited with one another, so B is connected to the positive of the output voltage, so Vb becomes V0, which is equal to Vs. Therefore, VSA becomes V0 minus 0 is equal to V0. Now representing your value of VSA, which is V0 in this period. Since V0 is a constant DC voltage, what I will do is represent it by a straight line parallel to your time axis during this 1 minus d into t period. Next, we will find out the value of VSB. So VSB is equal to Vs minus Vb, and as you can see from the figure, S and B point are short circuited with one another, so both will have the same potential. Hence, Vs minus Vb will give you to be 0. Thus, what we do is represent VSB during this period 1 minus d into t as 0 by making the x-axis bold and marking it 0. Thus, next what I have done is completed my third region, which is nothing but the dt region, and it will be same as our first region, which showed that VL was equal to VI, IL was a positive slope of Vi by L, and so goes on and applies for the other currents and voltages. Now next question comes, what is the average value of the inductor current IL? There are two average or DC current in the circuit. One is your source current, which is Is, and the other one is your load current, which is given by I naught. Now look at the figure. If S is connected to B, what is the value of IL? The value of IL is nothing but Is. Next, if S is connected to A, again if you look into the figure, IL is nothing but your supply current Is. Hence we can conclude that even though when S is connected to B or when S is connected to A, the value of inductor current is nothing but a source current Is. Thus the average value of inductor current IL average is equal to Is. Thus if you look into the waveform of IL, I have used a dotted line to represent the average value of IL, which is nothing but Is, as calculated. This average value divides the IL figure into two equal halves. Let us consider the peak to peak ripple to be del IL as mentioned in the figure. Hence from the average value to the peak value, the gap will be del IL by 2 as marked. Next, what will be the average value of ISA? If you observe the figure which is drawn on board, the current flowing through ISA is nothing but Is. Hence the average value of ISA will be Is. Thus representing ISA average value by dotted line in the waveform as shown to be Is, and from the average value to the peak point of ISA will be obviously del IL by 2, and I have marked it in the waveform. Next, calculating the average value of ISB. Now when S is connected to B, you can observe that ISB is nothing but IC plus I naught, and you know that IC does not support any average current. Hence, the average value of current that is flowing through ISB is nothing but the output current, that is I naught. Thus, I have written ISB average is equal to I naught. So, hence I have plotted the ISB average. I have shown it by dotted line which intersects ISB into two equal halves. The magnitude of the dotted line will be I naught as calculated, and the peak point to this average value gap will be del IL by 2. Next, we have one more figure left, that is the waveform of IC. So in order to plot IC, what we will do is apply KCL in the above figure. What we will get, ISB is equal to IC plus I naught. So IC is equal to ISB minus I naught, where I naught is nothing but the output DC current. Hence, in order to represent IC, our reference is obviously ISB, and our ISB is drawn in the figure. So if we decrement ISB by a value I naught, or if we decrement ISB by its average value I naught, we will get the value of IC or the waveform of IC. Now I have drawn the waveform for IC. How will it look like? During the DT period, ISB is equal to 0. Substitute it in the equation. IC will come out to be minus I naught. And since I naught is a DC current, I have represented it by a straight line. And during the 1 minus dt period, what happens? The waveform is decremented by its average value, that is nothing but I naught. Hence, the IC figure looks as follows. Next, we have to determine which devices are to be connected in order to replace the single pole double throw switch. Now, if we consider the current ISA, it is a positive current, and VSA voltage to be a positive voltage. So, we had already studied positive voltage and positive current is supported by power electronics device called as MOSFET. Next, if you check the ISB current, it is coming out to be positive, but VSB voltage is coming out to be negative. So, the device which supports positive current and negative voltage is nothing but diode, as discussed earlier. So, we will replace the single pole double throw switch by a MOSFET and diode connected between S and B terminals, and MOSFET connected between S and A terminals respectively. Thus, over here I have replaced the single pole double throw switch with a MOSFET and a diode. So, the circuit drawn on board is your actual boost converter circuit. Thus, I have completed the explanation of the circuit operation and drawn for you all the relevant waveforms that you will be needing. Next, what we will do is derive all the necessary equations of the boost converter. Now, let us find out the input-output voltage relationship. How will you find out? By applying volt-second balance of inductor voltage VL. So, as you can see from the diagram drawn, during DT period the inductor voltage is Vi, and during 1 minus dt period, the magnitude of inductor voltage is V0 minus Vi. Hence, both the areas will be equal. Thus, we can write Vi into dt is equal to V0 minus Vi into 1 minus d into t. Now, let's start with the calculation part. The t cancels out on both sides. Bring Vi on the right hand side and 1 minus d on the left hand side. You will get d by 1 minus d is equal to V0 minus Vi by Vi, which gives you V0 by Vi minus 1. Hence, V0 by Vi is equal to d by 1 minus d plus 1, and that gives you 1 by 1 minus d. Thus, from here you can write down V0 is equal to Vi by 1 minus d, where Vi is your input voltage and V0 is your output voltage. Now, how can you say this equation is for a boost converter or a step up converter? Now, if you substitute any value of Vi, suppose over here I have taken as 2, take any value of d, over here I have taken as 0.5, do the calculation, how much you will get? 2 by 1 minus 0.5, that gives you 2 by 0.5 equal to 4. So, your output comes out to be 4 volt and your input is 2 volt. As your output is greater than your input, it can be called as your boost or step up converter. Next, finding out the input output current relationship. We will follow the same procedure. Consider the converter to be 100% efficient. So, V0 I0, which is your output power, is equal to Vs Is, the input power. So, from here you can write down I0 is equal to Vs Is by V0. Substitute your Vs in terms of V0 according to what we have derived over there in the last equation. So, from there you can write down I0 is equal to 1 minus d into Is. So, next our focus will be in calculating the ripple current through the inductor, that is del IL, and the value of the inductor. So, we know that VL is equal to L di by dt, and di can be written as del IL, which is the ripple current in the inductor, and dt is the time period for which the del IL is occurring. So, we can take any period, either dt period or 1 minus dt period. So, I have taken the dt period over here and substituted in terms of dt. Now, del IL from here can be written as VL dt by L. During the dt period, what is the value of VL? Vi, substituted it, and we can write t is equal to 1 by f. Thereby, del IL will give you dVi by FL. And from here you can write the value of inductor, L is equal to dVi by F del IL. So, our next objective is to find out the value of capacitor C and the ripple voltage del Vc. As you all know, del Q is equal to C del Vc. Now, del Q is the amount of charge that is stored in the capacitor in one half cycle. So, if I take the period dt, so area under the curve will give you I0 into dt. We are taking magnitude, so we have removed the minus sign of I0. That is equal to C del Vc. So, from here you can directly write down del Vc is equal to d I0 by Fc. What is F? Is equal to 1 by T. So, T has been replaced by 1 by F. So, from here you can again write down C is equal to d I0 by F into del Vc. So, the Eth equation which we will write down now will be addressing to the boundary condition. So, the first boundary condition applies to the ripple in inductor current. So, del IL is equal to twice I0. From here I0 can be written as V0 by R, and again V0 can be written as Vi by 1 minus d. So, it becomes 2 Vi by R into 1 minus d. Del IL we have already calculated, that we are substituting in the next step, that is dVi by FL. Instead of L we are writing LC, because our inductor now is called as critical value of inductance. So, from here LC comes out to be d into 1 minus d into R divided by twice F. Next, we are finding out the critical value of capacitance by applying the boundary condition to del Vc. So, at the boundary condition, del Vc will be equal to twice V0, and V0 can be written as 2 into I0 into R0. So, thereby your Cc, which is your critical value of capacitance, can be given as d by twice F R0. Next, we will calculate the value of maximum inductor current IL. Please ignore the delta sign placed in front of IL max. So, that is why I have written in red that it is actually IL max, not del IL max. So, IL max is equal to the average value Is plus del IL by 2. And again IS was calculated out to be I naught by 1 minus d. So IL max can be written as I naught by 1 minus d plus del IL by 2. Now let us calculate the switch ratings. First I will replace all the AS terms by SW, which means switch. So IAS has been written as ISW and VAS has been written as VSW. From the waveform only you can understand that VSW should be greater than V0 and ISW, which would be the maximum value of switch current, should be greater than IS plus del IL by 2. Now the diode ratings will replace all BS by D. So IBS has become ID, the current through diode, and VBS becomes the voltage across the diode, so VD. So peak inverse voltage of a diode should be greater than V0 and ID maximum value should be greater than IS plus del IL by 2 from the waveform. So here we have come to the end of our lecture number 4, which was on boost converter. Hopefully students, you have understood the boost converter, how it operates, how I had drawn all the relevant waveforms, and all the equations that I have written down and derived step by step are very important for you to remember so that you can solve any problem related to boost converter. So guys, if you have any doubt regarding the operation and analysis of boost converter, please ask your questions in the comment section that is given in my YouTube channel after the video. I would be happy in answering all your questions and clearing all your doubts related to boost converter. So my next lecture would be on buck boost converter, which can be also called as step up down chopper. We will be analyzing the buck boost converter in the similar way as we have done in analyzing our buck converter and a boost converter. Generally, I would like to add one point over here. These circuits which we are studying are called as converters, that is buck converter, boost converter or buck boost converters. If you refer to books, there may be some circuits called as step up chopper, step down chopper. Both are same circuits, don't need to worry. But when we are calling it as a buck converter, that circuit uses a high frequency switching device, that is either a BJT or a MOSFET or a IGBT. When we are calling it as a chopper, either step up chopper, step down chopper or step up down chopper, then the switching device that is to be used is a thyristor. Once again, thank you to everyone. A humble request to all the listeners and students is to leave their valuable feedback in the comment section. I would also like to make a small request to all my viewers and listeners to click on the red color subscribe button below the video so that you are updated with all the videos that I post on my YouTube channel. Thank you. Happy learning. Stay home, stay safe.